Welcome to the Terminology Leading Practices stream of the SNOMED CT Expo for 2021. My name is Donna Morgan and I am a mapping terminologist at SNOMED International, and I will be moderating today's session. Please be advised that any questions or comments you may have on this topic can be submitted through the live Q&A in your AirTouch device. All questions will be answered at the conclusion of the presentation. So please allow me to introduce Warren Del Pinto from the University of Manchester in the United Kingdom. His presentation is entitled Computing Subontologies of SNOMED CT. I'll hand over to Warren now. Thank you.
Thank you very much. So yeah, as mentioned, the title of the talk is Computing Subontologies of SNOMED CT. And this is a collaborative project between the University of Manchester and SNOMED International. So I'll just get straight into things. So as mentioned, it's a partnership. I was working as a research associate, seconded to SNOMED International. And the full title of the project was SNOMED CT Content Extraction and Sharing. And this commenced last year in July and concluded this year in September. And on the slide there, you can see a list of the other people involved in the project. So myself, Renata, Yong, and Kai were all part of the working group. And the steering group, which we discussed with regularly, consisted of Rory Davidson, Jim Case, and Monica Harry. So thanks to everyone there, of course, for their involvement. And yes, SNOMED CT. So I'm sure we all know by now what SNOMED CT is. One of the most comprehensive clinical terminologies in the world. So there's a wide array of clinical information, and it's organized into different hierarchies. There's just a screenshot of the browser on the right-hand side there. So you can see it's organized into a collection of different hierarchies. And of course, there are modules for different domains, including the core content in the international edition, national and member extensions for different countries. And the main terminology, the international edition, as of July 2021, contains over 350,000 axioms and likewise for concepts. So it's an extremely extensive terminology, which is very advantageous in the sense that it covers what will be needed in many different clinical practices. But it does raise the question, how can users focus on specific content? So for a lot of specialist domains, there's a lot of specific applications associated with them. And not all the information in the SNOMED CT terminology is needed for every use case. So for different applications, we require different levels of detail from different domains. So from SNOMED CT, we might, for example, just need the content to do with renal diseases, to do with dentistry, to do with medicinal products. And each of these applications has different needs. So for some applications, there's already tooling out there for the use of reference sets. So these are a useful tool set to focus on subsets of SNOMED CT. And this gives you a customizable list of entities and their IDs to constrain data entry, search, querying, and analytics to the domain of interest. Does this cover every use case? Well, we would like to maintain semantics in some cases. So perhaps we don't just want a list of entities, but we actually want to maintain the meaning of those entities, their definitions, their relationships between each other, the polyhierarchy in SNOMED CT, things like post-coordination, non-ISA relationships via attributes like finding site or associated morphology. So all of this information is not present, of course, in a flat list. So we're looking at content extraction with respect to semantics as well. So there are a lot of existing methods for content extraction, and these exist to extract modules from ontologies. So modularization is perhaps the most widely known of these methods. And a module is a subset of the axioms in an ontology that preserves queries with respect to a given input signature. So say we supply a list of concepts to do with renal diseases, we would expect a module to contain some of the axioms from the ontology that maintain querying with respect to those renal diseases. And there are a lot of efficient methods for this, and one of the most available immediately for a lot of users would be locality-based modularization, which is available in the OWL API. So for example, you can compute star modules, top modules, etc., just directly using the OWL API. So while these are efficient, there are a few issues with respect to the use case we're discussing today. Modules can be very large, so particularly for a terminology of the size and scope of SNOMED CT, even if you restrict using a module, you might still end up with a very large resulting ontology, which is the form that modules take, as a standalone ontology in this case. So we need an approach that emphasizes conciseness. So we want to focus only on the concepts of interest. So whatever the user provides as input, we want to constrain our content to that set of concepts. So we also need interoperability with existing tooling. So it's no good if these standalone ontologies don't provide us with the kind of interoperability needed to use them in practice. So the project we've been working on, we want to extract content using a prototype we've developed over the course of the project. So this is now a complete prototype, which takes a set of input focus concepts, for example, a ref set of interest to a particular domain, and we generate a concise standalone subontology containing content related only to that input set. So the requirements here are based around those concepts. So we have the requirement to equivalently capture semantics of focus concepts in a standard compact form, and this is the authoring form. And we want the subontology to contain concepts other than focus concepts, which we call supporting concepts, and these are needed to define the focus concepts. So say you're interested in renal diseases, you want the supporting concepts that you need to be able to express the definition of those renal diseases. And we want to retain the relationships of those focus concepts, of that input set, without deviating from this compact, concise definition. So we don't want to have to construct a really verbose definition just for the purpose of capturing these relationships. The concept hierarchy should also be the same. So if you have a collection of concepts or classes in SNOMED CT, we want the subontology to retain that hierarchical structure without changing it. The only change that there should be is that it should be constrained to the set that we're interested in. So the transitive closure with respect to the original source ontology and the subontology of the hierarchy should be the same up to the signature of the concepts we're interested in. And of course, the supporting concepts that we bring in. And we want to support all the language features of SNOMED CT. So some of the more difficult ones include GCI axioms, reflexivity, transitivity, role chains. So there's been additional expressivity added to SNOMED CT over the years to express other clinical ideas. So we want to support all of those. So to give a quick example of authoring forms, the axiom or definition on the screen there, you have on the right-hand side, you have acute renal failure syndrome. And this is given an equivalent definition on the right-hand side. This particular example is not an authoring form. So we can see this by the fact that there is a primitive concept and a defined concept being used to produce the definition, whereas the authoring form just sticks to the proximal or closest primitive concepts for the concept on the left-hand side. And it also brings in the non-redundant attribute value relationships like finding sites and so on. So as part of the subontology extraction procedure, we extract an authoring form definition. So say if you give acute renal failure syndrome as your input set, then you'll receive a definition of this form. So we take the original definition in the source ontology and ensure that this is transformed into a standardized compact form. So here the defined concept has been replaced with the relevant non-ISA or attribute value relationships. So you can see two additional ones there. So this form captures the semantics we need. So it will equivalently define the concept on the left-hand side there while maintaining a standard format for definitions. So definition expansion, another aspect of subontology extraction is that in these authoring form definitions, you'll see all the blue concepts there are primitive concepts. And in this case, say, for example, they're not in the input set, then they're all considered to be what we call supporting concepts. So the idea is that these are brought in to maintain the definition of acute renal failure syndrome, which we assume was part of our input set. The question is, do we need the full definition of each of these concepts, or do we just need a partial definition? Is it really necessary to bring in all of the information about them just to maintain the definition of the concept we were interested in? So really, we want to be concise. So the concept highlighted on the slide there, which is measurement of renal function, is a supporting concept with what we call a partial definition or partial description. And this looks something like this. So taking the original description from SNOMED CT July 2020, you can see the axiom there states that measurement of renal function is a subclass of a measurement procedure which has a method attribute measurement action. In the subontology, however, we simply state that measurement of renal function is a procedure. And the reason being that we don't need the other concepts, we don't need the other information to maintain the meaning and relationships for our concept of interest, which was originally acute renal failure syndrome. So this is more concise. We don't need measurement procedure. We don't need method attribute. We don't need measurement action. These aren't specified in the input list, and they're not deemed to be necessary for the semantics of our input list, so we don't need to include them in the subontology. So these are two key differences between subontology extraction and, for example, modularization, where we don't just take a subset of the axioms, we actually transform them first into a standard form, and we can leave out definitions if they're not deemed necessary for the meaning of the concepts that the user was actually interested in. So subontologies, we mentioned we wanted to be interoperable with existing tooling. So of course for SNOMED CT, one of the other formats aside from OWL, which is the perhaps most common format for ontology files, we also have the RF2 format, which is the release format often used for SNOMED CT files. So this supports existing tooling. So we made sure that the prototype subontology extraction algorithm automatically produces on request both the OWL file and the RF2 format. And there are some additional steps that are needed for this to happen, which include things like computing inferred views of concepts, adding the additional metadata required for example, representing on the browser, and a collection of other things that are related to SNOMED tooling. So perhaps the most interesting tooling that this creates interoperability with is the subontology browser, which is a version of the browser that is now hosted at the link on the slide there, which hosts a collection of subontologies that were extracted for existing clinical reference sets. So, for example, the dentistry subontology takes the general dentistry ref set and produces a subontology using that as input that contains all of the information about that collection of focus concepts. The same for ERA. This is the European Renal Association, which you've seen an example from just previously. International Patient Summary, and nursing and health and activities. So there's a collection of subontologies you're free to browse on that link. And of course, we do welcome feedback. So there is a feedback button there, which links to a form with a collection of questions that would be very useful to have answers to. So we've already received some really helpful feedback from clinicians and other users. So yeah, we welcome as much feedback as we can get. It'd be very helpful. So just to take an example of this a bit further, going into the full edition, so the international editions browser in 2021, say I want to search for a fairly generic concept, a fairly high level concept like disease, then I find that I get 4,644 matches in around 2.5 seconds. So there's a lot of concepts sitting under here, which you'd expect. In the subontology browser, if I take the renal diseases subontology, so the European Renal Association subontology, I find that for the exact same search, I return 58 matches in 0.2, 0.26 seconds. So it's both faster to search, since there's less there to search, and the matches are more concise. So they're restricted to the diseases that are deemed to be related to the input set or are part of the input set themselves. You can also see this in the taxonomy view. So we have the full view on the left-hand side and the constricted view to the constrained to the ERA ref set on the right-hand side. So that's the subontology extracted for those concepts. And the numbers you can see just give an indication of the number of descendants of each of those concepts. So you can see at the top there, you can see the 350,000 or so descendants of the very top level SNOMED CT concept, whereas on the right-hand side, this has gone down to 490. For things like clinical finding, you can see that there's 114,000 or so, whereas in the subontology, there's 289. And again, not all of the sub-hierarchies of SNOMED CT are used in the ERA subontology. So just briefly nipping back to the full view there, sorry. You can see, for example, that clinical finding is needed, but record artifact as a sub-hierarchy isn't actually used at all, so it doesn't appear in the subontology. So it's not related to the concepts we specified as input. And this just expanding further, you can see the same thing for under clinical finding. It's a lot more constrained to concepts of interest. So a brief look at the size of subontologies. So I've mentioned a list of subontologies that are hosted on the browser there. And we can see that here we're comparing to star modularization. So I mentioned earlier star modularization being part of the OWL API. And across most cases, this is the smallest, kind of most concise module available from the locality-based module extraction methods. So we've got the ref set name on the left-hand side. The size is in the number of concepts specified in that ref set, and the resulting subontology size in terms of the number of axioms and the number of concepts. So the main takeaway here is just, for example, the Renal Association ref set I mentioned, the subontology contains about 480 axioms and 470 or so concepts, while the corresponding star module contains 3,000 or so of each. If I take another example like nursing, we're down to 2,600 or so, compared to the modules 5,500 to 5,700. And on larger subontologies, this continues to be similar. So for example, for IPS, we go from 12,700 axioms or so. Same for concepts, while it was 53,000 or so in the STAR module. So in almost all cases, this shows that the subontologies are more concise than modules. There are a few exceptions. For example, MP there denotes medicinal products, where we took a collection of concepts from only one hierarchy, so just medicinal products. And there you can see the sizes are much more similar. So there's a lot of interesting study to be done on when this occurs. But in this case, it's likely due to the fact that we're only really using one hierarchy in medicinal products. We're not spanning too much to other hierarchies. There's a few concepts from each from other hierarchies, but it's not as wide-reaching, for example, as maybe nursing or dentistry are. So there's a lot of advantage, especially when there's multiple hierarchies all being used at once. Subontology extraction really constrains those other hierarchies to only what we really need. So the emphasis is always on conciseness. And this makes things easier to navigate, classify, and query. So just to summarize the main benefits that we perceive with subontology extraction. As mentioned, they are self-contained ontologies. So it's not just a list of concepts. You retain the definitions, you retain the meaning, inferred relationships, the hierarchy between concepts, etc. And it's concise. So we're focusing on the concepts of interest only. We exclude any information that's not needed to give the meaning of those concepts. And as such, we maintain a much smaller ontology as a result. The benefits of a concise extraction method like this include ontology debugging and update. So for modelers and clinicians using the terminology, it's easier to examine and understand the semantics related to your domain if you don't have to navigate the entire hierarchy every single time you want to look through your concepts of interest. So for a domain where there may be diseases, there may be procedures, there may be finding sites and body structures, it's a lot easier to navigate through that hierarchy when you're looking at, say, 400 concepts rather than 350,000. Efficiency. So reasoning tasks like classification and querying, they take less time to execute naturally as the ontology gets smaller. So subontologies being concise, you can really expect all of these things to be much faster. Ref set improvement. So some of the feedback we received on subontologies so far pointed to what might be seen as missing content. So it might be expected that some information was present in the modeling, so in the definitions available, but wasn't actually present. And we saw this as quite an interesting application of subontologies. It allowed users to examine ref sets in terms of the hierarchy available to them, the definitions available to them, rather than just a flat list. So we noticed that domain experts were actually noticing potential gaps in ref sets that weren't previously expected. And this is purely because they could browse the subontology just like the main terminology. Ontology creation, so extracts are standalone ontologies. These, as I mentioned, they can be used as a starting point for an enhancement to existing extensions. So say you want to create an ontology specifically to do with cardiac diseases, you could extract content related to that and use that as your starting point. And content reuse. So since they're standalone ontologies and they are provided also in RF2 format, this means we can reuse content from the international edition or an extension in a different application. And while we constrain it, we can still expect that it functions the same up to the content we extract. So in summary, this has been a collaboration between academia and industry, which has developed an algorithm and a prototype for SNOMED CT content extraction, which conforms to the standards you'd expect for SNOMED content. And the list of potential and future directions includes things like fine-tuning subontology content to specific applications. So these include, for example, data entry and querying, wherein in data entry, it may not be advantageous to have very vague concepts like disease, whereas in querying, these kinds of group of concepts, these high-level concepts could be useful if a user is trying to constrain their query to a general group of concepts rather than having to engineer a specific query for really low-level concepts. Navigation, we can tune in a similar way. We might find that certain groupers help clinicians and modelers navigate their content. They may request additions to subontologies that can then be incrementally added. So this is all an interesting direction. Content sharing. So since we can extract parts of the terminology, it would be interesting to see how we could directly share this between extensions without necessarily having to request promotion to the international edition when this isn't preferable. So hopefully this should take some of the pressure off for modelers in some cases, and aggregating content. So it may be the case, for example, that you want to create a medicinal product subontology, for example, where you want to take medicinal products from all these different country extensions and aggregate them into one ontology just to do with that. So just to leave you with the contact links for us there, if you're interested in this work or you have any questions, feel free to email any of us. The subontology browser link is there available as well. So please do have a look and leave feedback if you're interested. And the GitHub repository, the code for the prototype is available there on the IHT SDO GitHub there, the link. So feel free to have a look. Thank you very much.
Thank you, Warren, for an interesting and well-presented presentation there with some really good supporting examples. Can I ask that all attendees give us a moment now while we switch from our pre-recording to pre-recorded content to live, so that Warren can address any of the questions that you've been submitting throughout his presentation. Please also note that this session will be live and available on the event platform for the next 3 months. Thank you. Thank you, and welcome everybody to this live session following the pre-recorded session. It's been a very well attended and interesting presentation. So a couple of questions already. First one from Feiger. What if two focus concepts have relations to supporting concepts that have a subsumption relation, for example, an excision or a surgical method? The focus concepts may then have a subsumption relation too. So how is that preserved?
Correctly, the definitions of supporting concepts will be based on whether or not they're required for each focus concept. So in the case where they have a subsumption relationship between each other, if you've come across a focus concept that is a descendant of them, and that supporting concept meets the requirements for needing a definition, for example, it's a defined concept as well, then its definition will be added based upon those focus concepts. So if you come to the second focus concept then, and that supporting concept definition is already included, then the check will confirm that that is already there. If I understand the question correctly. So if supporting concepts do subsume one another, then the two main things are that if their definitions are required, then they'll both be taken in according to the focus concepts. And if that hierarchy is present in the original ontology, then it will be present in the subontology as well. So that kind of subsumption relationship will carry over is the main requirement.
Fike, I hope that answers your question. Joe says, great presentation, Warren. Great to see the examples, and he thought the scenarios were very good.
Thank you.
A comment from Jay Kohler. Great work. So have you done any work on simply modularizing SNOMED CT top-level hierarchies into its own hierarchies yet? I'd have thought there is some complexity there, but this work could really enable that in some ways.
Yeah, I think that's definitely a question for the community once this, since this is now available. I think it does open up, it's a good point. I think it opens up new ways of considering how content is divided. So we've already seen that a bit with when expert users have come across subontologies looking at ref sets, they can already guide themselves through the hierarchy in a much more concise fashion and kind of see gaps in ref sets. I do wonder if that's another application that might be quite promising is noticing reorganizations of the hierarchy. If you can shrink the hierarchy down to this concise set, you might notice that some groupings should or shouldn't exist. And perhaps one area we did look into, which I think is promising future work, is computing grouper concepts based on user needs. So I think in the talk I mentioned different applications like querying and data entry, and these naturally have different navigation requirements. So it might be the case that you want to organize your hierarchy based on useful grouper concepts that aren't present in the standard international edition, for example. So that might be an example of computing a new hierarchy by grouping concepts under a, say, for example, a useful querying grouper. That might be a good direction.
Jay follows on from that comment, Warren, and says, yep, that's what we used to do when I was sorry, I can't see the whole comment. That was what we used to do when I was working at the University of Manchester with Alan Rector. Love to collaborate. So that's something you can take forward, I'm sure. Another question from John. John Snyder, has any thought been given to distribution licensing for subontologies, and how that would change from an affiliate license, or will subontologies be distributed under same license as the global patient data set?
So naturally, this is a question. I think if you've seen Yong's email there, it would be good to get in touch with SNOMED International regarding licensing. The conversation is a very good question, and the conversation has come up a few times. Since this content is separate from the international edition and can be computed from extensions and so on, the requirements for checking the content in subontologies and applications building on subontologies and so on obviously opens up a bit more complexity. If you start having these subontologies around, users need to be aware that they aren't subject to the same content modeling guidelines necessarily, and they're not checked as thoroughly necessarily as, for example, the international edition. So I do think naturally with more capability, I think that you need to consider new options for distribution, and version control is another challenge that I think checking which version of the source ontology, so for example, SNOMED International edition, which version of that was used to compute a subontology. All this kind of tracking, I think, is absolutely necessary infrastructure that will need to be built up. So.
And I think what looks like a final question, how do the techniques of modularization, such as the methods available in the OWL API and subontology extraction, differ?
Okay, so yeah, they are very, very related methods. I'd say that the two take a seed signature of concepts. So in that they are similar. So they take those initial input concepts and aim to extract content to do with those concepts. The difference starts showing in how you treat the additional concepts. So modularization, for example, star modularization, top and bot modularization, available in the OWL API, aim to compute a subset of the original ontology. So these will be a collection of axioms extracted from the original ontology. And the aim is to compute, to gather these axioms effectively until you have a set that keeps all of the entailments of that entire collection of concepts, including the ones that have been brought in over time. The subontology extraction instead focuses more tightly on the focus concepts, so the input given by the user. We're not aiming to preserve all of the entailments of the supporting concepts. Specifically, we're aiming to compute the definitions equivalently for focus concepts and maintain their relationships, but less so for supporting concepts. And this is where the conciseness aspect comes in. We don't need to drag in the definitions for supporting concepts in that way. The other main difference I would say is that that it's not a subset of the original ontology necessarily in subontology extraction. Since we compute the definitions in a standard authoring form, it may be the case that the original axioms are transformed into this equivalent form, which is not the case in modularization. That would be bringing in the original axioms, at least in the OWL API tools available.
Just one final question that's coming quite late, and hopefully you've got time to answer this, Warren. John says, I may have missed it. Can you speak a bit more about how the extraction tool functions? Is it ECL query based?
So it's not ECL query based, but it does. So you can run ECL queries in the browser. So the main aspect with the way that the algorithm works. If you want to dig into this, the code is, as I say, is available on GitHub. But very briefly, the idea is that you need to identify which supporting concepts matter to preserve relationships for focus concepts. So, for example, the concept hierarchy. If you have a subontology containing a bunch of concepts, including focus and supporting, you want to be able to maintain that hierarchy without editing the definitions of focus concepts. If you start adding subsumption relationships explicitly, then you end up with a very verbose, bulky definition for focus concepts that's very difficult to navigate. So the idea is to identify which supporting concepts need definitions to preserve those relationships and infer them automatically using a reasoner. So, for example, an obvious one would be if you have a supporting concept that is a parent of a focus concept, and that supporting concept is defined, then naturally its entire definition might be needed to infer a parent relationship for the focus concept sitting beneath it. Other rules are around language extensions like role chaining and transitivity and so on. So as I mentioned, if you want to dig into that, then the code's available.
Okay, well, thank you for that. That really concludes this live session, and you've crammed a lot into the final few minutes there for answering questions. So thank you, everybody, for attending today. Thank you, Warren, for an excellent presentation, and it will be available live on the hub. Thank you very much.